Number one, what is the unit for magnetic field? It is a Tesla. Oh my gosh, got stuck on my glasses. Unit for magnetic field is the Tesla. So if you look that up, hopefully you found the right one.
What does SI mean?
Scientific unit. Or it's like standard international. It means scientific unit.
That wouldn't be the answer.
No. Tesla is the SI unit for magnetic field. So what is the equation to find the strength of magnetic field around a wire? It is this. B equals mu naught over 2 pi times I over R. So if you looked that up and found it, I am very impressed. Yeah, so let's talk about what each of these things are. So B is magnetic field. Yep. I is current. So we're just all kinds of things that are totally what you would think that letter stands for. R is radius. That one makes sense. And if you're wondering why radius, it's because we're looking for the magnetic field around a wire. So if here's my wire, I'm looking for the magnetic field that's going around it. And so the radius is how far out from the wire it is. Which brings us to this guy. It's the Greek letter mu, but it's not just mu, it's mu naught. That's what the little zero next to it means, not. So it's mu naught. It is, and I'm not making this up, called the permeability of free space. Yep. The permeability of free space. It is my second favorite physics constant, just because it's such a ridiculous name. The permeability of free space. Here's what it means. It means how well do magnetic fields go through space. That's what it means. The permittivity of free space, which is how well electric fields go through space.
Why is that one?
Well, because permittivity sounds better than permeability. Permeability is like permeable is like a word you've heard of, but permittivity is not a word that you've heard of.
The permittivity of free space out there.
Yeah, now you've heard of it.
I hear it all the time.
It has to do with it's the root word is permit. So we're Isabel, we're on the front page of practice that I gave you last class. All right. By the way, permeability of free space is a constant, which means it needs a value, and that value is you're going to laugh at it. 4 pi times 10 to the negative 7th. Yep, the constant is 4 pi times 10 to the negative 7th. But now you might be saying to yourself, why on earth would they leave it like that? And here's why they left it like that. Why didn't they multiply 4 and pi and get a number? They left it like that because, oh, look what it's over. It's over 2 pi. So the 2 pi and the 4 pi will cancel, and you'll be left with 2 every time. Makes the math easier. The real reason they left it that way is because physicists don't care if it's easier for you. The real reason they left it that way is because it's more accurate to say 4 pi than it is to say 12 point whatever it is.
So basically, that entire equation is literally B to times I over R.
Yeah. Yeah, that's what it is.
Because physics.
Well, it's 2 times 10 to the negative 7. Don't forget the negative set, the 10 negative 7. All right. So number 3, what is the magnitude and direction of a magnetic field 0.2 meters away from a 2 amp wire that is going into the page? So this is called the first right-hand rule. So let's start with our equation. B equals mu naught over 2 pi I over R. So what are we given? We're given what is the magnetic field, so we're solving for B. 0.2 meters away, that's the radius. 0.02. A 2 amp wire, that's the current. Going into the page. We'll get to that later. So, B equals mu naught, which is 4 pi times 10 to the negative 7th, over 2 pi. So the 2 pi cancels with the 4 point to give me just 2. Times 2 over 0.02. Got 2's galore. Indeed. So 2 times 10 to the negative 7th times 2 divided by 0.02 gives me a magnetic field of 2 times 10 to the negative 5th. Two times 10 to the negative 5th Teslas. Now you might be saying to yourself, hey, Mr. B, you told me to find the magnitude and the direction. I noticed you didn't find any direction there. Must mean that I don't have to do it, and it's not a problem. No, we need to do it. So, a wire going into the page. So I'm going to draw a wire going into the page, and the way I do that is I draw a circle for the wire. Into the page is an X. By the way, out of the page is a dot. So, we need some way to figure out the direction. And here's how we do it. It's called the right-hand rule. Right-hand rule looks like this. You take your right hand. Okay? You stick your thumb out. You wrap your fingers around it so you get something like this. Kind of like a fist almost. Okay? Then you stick your thumb in the direction of the current. It's going into the paper. And now I look at my fingers. What direction are my fingers going? Yeah, that's the answer. That's it. That's it. That's it. You take your thumb, you stick your thumb in the direction of the current. What's the direction? Clockwise. What if it was coming out of the paper? Counterclockwise. Bray is unconvinced.
Oh, so that's where the fingers go in.
What about the left-hand rule?
No left-hand rule. Okay? Left-handed people don't count. No, it's not true. Obviously, I love left-handed people. They are wonderful human beings. Then we'll set up a system to help you. But you don't have 2 left hands, so you're fine. Okay? So, look at the direction that your fingers curl, and that's the direction of the field. The reason why it's called the right-hand rule is because the left-hand rule would be backwards. Okay? So it's the right-hand rule. Okay? So here's the direction, clockwise. Here's the value, 2 times 10 to the negative 5th. Questions? Flip her over.